Good morning or good afternoon, everybody, and thanks for coming along to today's presentation, which is going to I'm hoping you can see
Yes,
my
that's great,
presentation.
Daryl.
Is that
We can
okay
see
there,
you.
is it? I'm just going to put that out of the way.
Yeah, that's great. We can see you, Daryl.
Right, okay. Right, yes, good morning, good afternoon, everybody, and thanks for coming along to today's presentation. Today's presentation won't be a long one, probably about 30 minutes, and I'm going to talk about carbon dioxide absorption and as well as diffusion under humid operating conditions. And really we'll be talking predominantly around competitive adsorption processes under what I would describe as real-world process type conditions. And this is the work done by Paolo, one of my PhD students at Imperial College, who's working on this area of CO2 capture and diffusion. So I think it might be useful just to give a bit of a strategic background to this topic. I think it's it's something you'll be familiar with if you're working on CO2 capture, but it's worth making a couple of comments then really around the background. There are currently about 51 large-scale CCS facilities around the world, and about 19 of those are fully operating. And we need about 2,000 of these facilities operating to achieve the global climate target we have in terms of removing CO2 from the environment. So we really do need a large number of these CO2 absorption instruments, instrumentated-based methods for capturing CO2 in the future. And although at the moment, most of the technology used industrially is based on liquid-based capture, there's increasing interest in the use of gas phase adsorption, so solid-state adsorbent materials to capture CO2 going forward. And really the discussion I will make with you today is really around what are the right sorts of experiments to conduct if you want to understand the CO2 capture behavior of materials, particularly under what I describe as real-world conditions. So if we look now, if we look at a lot of the computational simulations that are available, and they're becoming increasingly important, there's some excellent simulation work being done, but there is a lack of experimental data for validating some of those modeling work, and particularly experimental data that relates to the actual environmental conditions under which CO2 capture actually occurs. And certainly, as well as that, there's some data available on mass transfer resistance and diffusion for new solid materials, but it's relatively scarce, relatively scarce in terms of what's available in literature. I mean, I think it's fair to say that there's an overall need for fast and accurate characterization techniques that can provide crucial experimental information on solid-state adsorbents, which combined with molecular simulation and process scale modeling are needed in order to move forward the next level of technology readiness for these sorts of materials. From a practical perspective, if we're looking at CO2 capture, from an industrial perspective, it's always the case that CO2 is never the only chemical present species. However, if you look at the papers published, something like about 95% of the papers published simply consider CO2 absorption all by itself. But actually, in real industrial carbon capture, it's much more complicated. And there are more species present, particularly in the flue gases that come off a power station that's fueled by gas or by coal, for example. Certainly, you're going to get water vapor present. And typically, in the gas phase, you're going to see somewhere between sort of 5 and 50% of water vapor present. You're going to see various nitrous oxide type products between 100 to 400 ppm. As well as related sulfur dioxide and trioxide products at a higher level, 120 to about 1600 parts per million. So all these species that are present are effectively going to be competing with your CO2. So it's not just a problem in single component CO2 absorption, it's much more complicated than that. And really what you need is really fast and accurate characterization techniques that can replicate the real world industrial scenarios if you're trying to get optimum absorbent materials. So certainly measuring CO2 capture by itself is interesting, but if you want to get closer to the operational needs of a process plant, you need to be able to consider other species such as water vapor. And today's presentation will consider both water vapor absorption and CO2 vapor absorption on some classes of new MOF-based adsorbents. The technique that we'll use for quite a bit of the work is a technique known as dynamic vapour sorption. It's a gravimetric technique that can be used to characterize solid-state materials under a range of industrial relevant conditions. So we're going to certainly look at that technique today. and we're going to measure effectively some CO2 absorption and desorption on some novel MOF materials in the presence of water vapor. And we're also going to do some experiments involving the determination of the diffusion constants, because if we're looking for processes where we've got CO2 adsorbing onto surfaces, then understanding the rate at which CO2 diffuses into the materials and is absorbed is critical. So we're going to use some of the DVS data we see today to essentially give us some information around diffusion constants. As I'll describe towards the end, although gravimetrically we can determine a lot of information around CO2 absorption in the presence of water vapor, there are some experimental conditions where the gravimetric techniques are more difficult. And I'll describe a new technique that we're developing based on breakthrough analysis, which is a slightly more robust and well suited for studying true competitive absorption and co-absorption phenomena. That'll be the last part of my presentation today. So maybe to start with, just a very brief recap on some sort of vapor absorption science. When vapors such as CO2 or indeed water vapor are brought into contact with a solid surface, some molecules will attach to the surface and will form an adsorbed layer, and some of them may diffuse into the bulk of the material. And as we increase the concentration of water vapor or CO2 vapor, more molecules will adsorb or absorb on the material. And I'm showing you here just a simple graph which is simply showing the amount of material that's been adsorbed. So it's a percentage increase in mass that's shown over here on the left on the y-axis. On the x-axis, we're looking at the concentration, in this case, of water vapor molecules, and we refer to the percentage RH. Of course, if it was CO2, we'd be talking about the partial pressure of CO2. This is just a generic adsorption and desorption isotope, and you can see that there's a period in the middle called hysteresis. In other words, when we do adsorption and desorption, we have a more complex phenomena. So there are conditions under which the materials and the adsorption processes give a difference in the adsorption and desorption behavior. And if we're doing water adsorption, for example, often we're looking to understand the following potential processes. We're looking to understand monolayer adsorption. We may be looking at multi-layer adsorption. Sometimes the vapors or gases might condense into pores. We can sometimes be interested in bulk absorption where it dissolves inside the material, or in other cases, hydration reactions. So by measuring the vapor absorption information, we can get a fundamental understanding about the sort of processes at a molecular level by which the vapor molecules or the gas molecules are captured by the solid state material we're investigating. And again, just to help remind you a bit about the technology, if you're not familiar with it, we're going to take a small sample, and the sample will typically be 10 or 20 milligrams of powder. We're going to weigh that very accurately in a microbalance. And during the experiment, we're going to monitor the mass, and we're going to change the partial pressure or the humidity of the gas phase or vapor phase species we're using. As we change the concentration of water vapor or CO2, the mass will change. If the concentration goes up, the mass will go up. If the concentration goes down, the mass will go down. So we're going to get a basic kinetic plot, which is typically for us weight versus time. As we step up the partial pressures or concentrations, the amount of gas or vapor in the solid will increase. And we're going to measure that. And from the kinetic data, which is the raw data from these DVS experiments, we will end up getting an adsorption isotherm, which is a measurement of the amount of material adsorbed, typically in this case given in weight, versus the relative humidity, which is given in the x-axis. So this is just a little bit of background that some of you might find helpful. As far as the instrument, there's just a picture of an instrument. It typically will run a 10 to 20 milligram sample is typical, though we can run bigger samples, and we can set that up automatically to measure the isotherms we want. So let me start by just showing you some typical kinetic data we would obtain for a material. So what I'm looking at now is looking at a MIL 101 based material, and I'm showing the kinetic data. So we are showing in the blue steps, we are increasing, in this case, it's the water vapor isotherm. So we're increasing in about 5% steps the humidity that the sample is exposed to, and the red trace is the increase in sample mass. So as the humidity goes up, the mass goes up. And you can see if we continue this experiment on, and at each step we wait for the sample to achieve a mass equilibrium, we effectively have a measure of both the kinetics at which the water molecules go into the material and also the equilibrium concentration. And you can see for this MOF, and the experiment's done at 298 Kelvin, and 1 bar, we're having about an 80% increase in mass, i.e. if I started with 10 milligrams of sample, by the time I get to 90% humidity, that sample's increased by 80% and now weighs about 18 milligrams. And that experiment took about 2 days to run. So that's a typical experiment for a single component system. But as I said to you before, in the real world, of course, if we're doing CO2 absorption, we often have water vapor present. So the question would be, how does this material behave if I was to expose it to a humidity and then introduce the CO2? So this is a pseudo competitive absorption problem. So we are effectively assuming in this particular case that the water vapor absorption is effectively irreversible, or rather the CO2 molecules are not going to displace any H2O molecules. And for some systems, that might be a reasonable assumption. But later on, we'll look at some methods where we don't need to make that assumption. But in this case, we're assuming that the H2O absorption is relatively strong. And when we introduce CO2, it absorbs but does not displace the water vapor. So let me look at the data I'm showing you here. So again, this is a MIL 101. This one is fluorinated with about 1% fluorinated groups. And on the y-axis, we've got the increase in mass, which is shown here in percentage, which is relatively low. We saw 80% before. We're seeing much lower levels at the moment. And we're looking on the red traces, we're looking at the mass changes. So we introduce a small humidity to start with. It's a low humidity, it's only about 4 or 5%. So we introduce a small amount of humidity, about 5% here. And the first curve at the front shows you the uptake of water only. And you can see that is picking up about 4%, just over. I then introduce a 10% vapor stream of CO2. So I've now got CO2 and water vapor together. And you can see there's a small but clear increase due to CO2 absorption. So in other words, we've got water occupying many of the sites in the material. Probably about 80% or plus of the sites are occupied by water vapor, but the CO2 vapor is able to take up another maybe 5% of the site. So we are able to work out how much CO2 is absorbed when the sample has already got a relatively significant amount of water vapor in it. So this is a sort of pseudo two-component or the two-component experiment where we're doing essentially pseudo competitive absorption. And for some material sets, that is quite useful. So here we've got some single component results. Here are the water absorption isotherms shown on the left-hand graph. That's taken from the previous data you saw before. And as I said, we have up to about 80% water uptake. And here on the right-hand plot, we're plotting the CO2 absorption, okay? And this is CO2 by itself. In this experiment, there's no water vapor present. And the units given here are millimoles per gram. So it's basically giving you a linear isotherm. There are two different MOF materials here. The traditional MOF 101 is slightly higher uptake for dry samples, i.e. CO2 only with no water vapor. And the second material, as I said, is a slightly fluorinated MOF 101. But of course, it's a bit more interesting to consider the case when actually we've got two components. So in the experiment we're doing now, we're looking at the amount of CO2 is captured, but when the material has had different exposure levels of humidity. So in other words, we take the solid state sample, and there are 4 different solids we've characterized here. And we initially expose them to a certain amount of water vapor, and in one case it's no water vapor, then it's 5, 10, 15, 20% humidity. And in each experiment, we then evaluate the CO2 absorption at about 10%, for about 5% CO2. And what you can see here for the material on the left, which is HCUST1, it's got very good absorption in dry CO2. But as soon as I introduce CO2 at a high humidity, in the case 20%, its performance substantially drops. And for MIL 53, it's even a more substantial drop. So as I said, what you can see here is that we're able to see the decay in performance as we introduce high humidities. But you can see, however, for MIL 101 and for the MIL 101 variant you see here, that MIL 101, which is an overall more hydrophobic material, it is less affected by humidity. So certainly, so for example, at 20% humidity, we can see there that the MIL 101 and indeed the MIL 101 modified offer superior performance to the MIL 53. But you're able to look now at the comparison between CO2 adsorbed in the dry state, as most people do, and also in comparison with materials, in comparison when the presence of water vapor is increasing. And this just shows a little more detail, the data sets for the MIL 101 and the fluorinated MIL 101. And we can see here that the performance is actually very, very similar, but there's a few intermediate humidities. At about 5, 10, 15%, the fluorinated material has slightly better performance. So it's not amazingly better, but just slightly better. So you can see there that the fluorination has slightly improved the performance. The other thing which is also be interesting to study is what happens under long-term cycling. We're not going to talk about it today, but one of the concerns is for many capture materials, if they're cycled many times, if they're exposed to water vapor, are they going to be stable? Degradation of adsorbent is a concern in many process considerations. So one of the things you can do in the DVS is you can take the material and you can cycle it multiple times to check whether it maintains its CO2 absorption capture as it cycles through moisture uptake multiple times. And that gives you some idea about how it might perform in an industrial setting. So this just gives you some information about uptake. So we're now going to talk a little bit about diffusion. And one of the things we're concerned about is trying to understand how diffusion is going to contribute to the process performance of our materials. And we're just understanding how the molecular diffusion of CO2 will occur as it passes through the materials that we want to use for capture. So it turns out when we want to do diffusion, essentially there are some fairly simple analysis based on Fick's law, which allow us, if we're able to measure the mass as a function of time versus the mass at time infinity, and we know something about the dimensions of the material, we're able to work out to a first order what the diffusion constant is, the rate at which the material enters the material that we're looking to do the adsorption processes on. So experimentally, what does this look like? So what we're going to do is essentially look at the mass as a function of time. And every time we do a step in a DVS experiment, we're getting mass as a function of time. And what we're going to do is essentially take the Fick's laws equation to the data sets, or we're able to linearize that in a fairly standard way, and that allows us to calculate the diffusion constant for CO2 adsorbing into a material. Now, of course, what we can do in our experiments is not just measure the CO2 absorption in the material when it's dry, but we can also measure CO2 absorption at different humidities. And of course, practically, the material that is undergoing diffusion, there will be background humidity there. And in the next table, we can actually see the diffusion constants for our material for different relative humidities. And what we can see here for the two different MIL materials is that there's some substantial differences in the diffusion constants. And indeed, at 0% humidity, the diffusion constants are relatively low for both materials. But interesting, when we go up to about 5% humidity, the diffusion constant goes up quite substantially. So essentially what we see here is that the presence of water vapor facilitates the diffusion of CO2 molecules into our material. So these bulk diffusion transport constants are quite interesting in terms of understanding the material's performance and how that will translate ultimately to developing processes. However, as I said very early on, one of the constraints in some of the gravimetric methods is that I assumed very much that we had pseudo-competitive adsorption, and that means really that the water vapor is effectively irreversibly absorbed. Now, of course, there are going to be many cases where that is not a fair assumption, and therefore we need to think about how we're going to fix that up. So the technique I'm going to talk about now, and it's not a new technique, we didn't certainly invent it, I didn't invent it, it's been around for many years, but we're refining this, and really we're looking to do what's called breakthrough analysis. And in a moment, I'll explain to you a bit about breakthrough analysis. But what it allows us to do, it allows us to generate a stream of CO2 and H2O simultaneously. They can be different concentrations. We will have a temperature-controlled environment. We will then take that gas stream and pass it over the sample. And we're going to look at the concentrations that enters the column and the concentration that exits the column, which is of course packed with our adsorbent. So let me describe very simply the experimental procedure. So it starts right where the gray section is here, where there is a sample holder, and that's essentially a small column. It holds probably 20 to 100 milligrams of powder, and in this case, one of the mill materials that we saw before. And what we're going to do is we're going to pass through that column a stream of typically nitrogen with both CO2 and water vapor. So in other words, if you like, it's a 3-component system: nitrogen, CO2, and water vapor. And pre-column, we have a sensor that measures the CO2 concentration, and we have another sensor that measures humidity concentration. So we measure the concentration of CO2 and water vapor that goes into the sample. It passes through my adsorbent, it exits, and we have another set of sensors that measures the concentration on exit. And essentially, by doing this type of configuration, we are able to work out when the water vapor and or the CO2 breaks through. In other words, at what stage is the capacity of my column fully exhausted, and now my CO2 and or H2O are no longer absorbed because the column is fully exhausted and it passes through and is emitted out the other side. So that's the methodology, and this drawing just shows you what we're talking about. So this is a time-based experiment, and we are going to measure concentration. So I'm showing you here a breakthrough curve for carbon dioxide. So just imagine I've introduced 5% of CO2 vapor into nitrogen. It's passing through a bed of, in this case, moth particles, and initially the moth absorbs all the CO2. And if you look at the left-hand curve, you can see from time 0 to time 600, we see no concentration of CO2 because the CO2 is being absorbed by my adsorbent. That's what you'd expect. But after that material is fully saturated, then we start to get breakthrough, and the CO2 will increase, and eventually you'll come up to the concentration that's entering the column. And from the area under the curve here, I can work out, if I integrate this area, I can determine the number of moles of CO2 that's been captured, and I know the concentration, so effectively I have a data point for an isotherm. Now, of course, this has just been done for CO2, but actually we can do a simultaneous measurement for water vapor, and that's what we do. We have 2 detectors, one does CO2, one does water vapor, and that allows us to actually monitor the CO2 breakthrough simultaneously with the water breakthrough curve. So here is an example data set. This is using HCUST1, and here are the breakthrough curves. Here, there is a CO2 breakthrough curve shown in the green, and that breaks through quite quickly. The breakthrough there is only in a matter of about 5 minutes. It's a very quick breakthrough. The blue shows you the breakthrough for the water vapor, and the water vapor capacity is much, much greater, and it takes 1,500 minutes for that to break through. So what this says is that the capacity for the material for water vapor is way greater than it is for CO2. However, we already know that. But in this case, we can do true competition. So if there was a displacement between the CO2 and the water vapor, these peaks will allow us to quantify that. So that's why the breakthrough curves are interesting. It allows us to look at displacement phenomena, so true competition can be done. So in this particular experiment, we have 10% humidity and 10% CO2, and the flow to the experiment is 10 mils per minute and done at about 25 degrees. So it's a nice technique, doesn't require a lot of sample, but allows us to do problems where there's true competitive adsorption. And we can integrate the areas under the curves, and we can work out the uptake of CO2 and water vapor from these curves. So it allows us to effectively get similar information to an adsorption isotherm you obtain from DVS, but allows you to do this under true competitive adsorption conditions. So that has some benefits. So I think that's about half an hour, and I was only planning to speak to you for half an hour. So the final conclusions today are that the DVS is a fast technique for providing researchers with accurate experimental data for rapid screening for CO2 absorption. By fine-tuning MOFs, we can enhance CO2 absorption, even in the presence of low levels of humidity. If we want to determine CO2 diffusion constants as a function of water vapor, that can be done gravimetrically. And breakthrough analyzers is an exciting way of measuring quantitatively true competitive adsorption and co-absorption. I thank you for your time and attention, and I'll be happy to answer any questions that you might have. Thank you very much.
Thank you again, Daryl. It's a great presentation. We have a few questions here, and before we start, I would like to remind everyone that you can submit your questions through the questions panel on the GoToWebinar kind of interface. So please, if you have any questions for Daryl, please submit them now. Our first question, Daryl, from Aravind Viraya Rabindran. Is it possible to measure diffusivity of carbon dioxide in liquid using this instrument?
It could be done, yes. Providing you, yeah, I'm just thinking how, yes, you could do that, yes, if you set up, providing the liquid isn't too volatile, okay, so in other words, providing the vapor pressure is not too high, there's no reason why you couldn't create a sample with a well-known geometry, expose CO2 to it, and look at the rate at which CO2 dissolves, e.g. and diffuses. So in short, you could do that, yes. If you said to me, have I got data to show you on that? I don't have it, but it could be done.
Okay, a question here from Daryl Jan. He says, it looks like you get useful data from the gas and RH sensor without the need of the microbalance. Does the microbalance contribute anything else?
It depends on the differences between, there are two different measurements, but they both involve the generation of flow at the front. The difference will be the accuracy. The gravimetric instrument is going to be more accurate in terms of total mass uptake. And the reason for that is if you're using the breakthrough analyzer, you have to integrate the detector signal. And any integration effectively carries a larger error burden with it. So the gravimetric technique will actually be more accurate, but has a constraint that it's difficult to do with true competition. The breakthrough analyzer can do true competition, but slightly less accurate because you have to integrate the signals.
Okay, great, thank you. A question here from James Hall. Have you considered testing, he says hi as well, have you considered testing O2 in the synthetic flue gas mixture to evaluate the competitive absorption of O2 versus CO2 versus H2O?
Sure. The short answer is we haven't done that. I mean, in the case of the breakthrough analyzer approach, you just have to have a detector present to do the species you want to study. So providing, if you wanted to add an oxygen sensor to the system, which could be done, you could do that experiment. And that's where the breakthrough method becomes more interesting, because even doing two components is slightly tricky gravimetrically, even though you get very accurate data and you can use a very wide range of components. When you get to even more real-world problems of the sort that James describes, you might have 2, 3, 4 components, and that becomes really challenging gravimetrically. But if you can put in your system appropriate sensors, and O2 sensors are relatively easy to get hold of, you can potentially do all those species at the same time. So we haven't done it, but it could be done using breakthrough analysis.
Great. A question here from Luke Woodliff. He's asked, is it possible to also account for gases like NO2 or SO2 concentrations in the flue gas?
Yes, it can. I mean, in the system that we're in the breakthrough analyzer we're running, we have got a PID sensor, and that's sensitive to the nitrogen compounds. I'm not currently if it's sensitive to the sulfur compounds. So you can do those with the breakthrough analyzer, and you can do those also gravimetrically. Okay. Again, it's just a question: is it a single component measurement, or are we doing, CO2 and water vapor and H2? It just depends how many components you got as to how complex the problem is. But those sorts of materials could be done either gravimetrically or using a breakthrough analyzer. But again, depending on how many components and the complexity would probably steer you to one method or the other.
Thank you. A question here from Nick Filstra. Can you talk about what the dead volumes before and after the sample column are like, and how significant are they for this instrument apparatus?
Yeah, fine. That's a really good question, Nick. Thanks for that. We are able to. There's a few ways you can. The dead volume is essentially what you might describe, if you're familiar with gas chromatography, it's the hold-up volume. It's the volume in the system that doesn't contain sample, and it's essentially something we have to measure in the column. So if I go back here, just a couple of slides, we don't show it. So at the moment, although we haven't shown it here, there's a certain amount of time at the start of the experiment where nothing can possibly break through because we have to determine the dead volume. So I think certainly the dead volumes in these systems, as I recall, are less than 1 cc, and we have some experimental protocols to measure them. So we do have to keep an eye on them. You do want to keep them minimized, but we are able to manage those fairly well. And one of the reasons we're able to manage them fairly well is that we have a lot of experience doing inverse gas chromatography, where dead volumes are also an important measurement. So we're certainly familiar with it. We can measure it. We didn't talk about it today, but in the future, I will do a presentation just on breakthrough, and I'll explain in detail how we measure those dead volumes. But they are important to measure to get, and it will affect the accuracy of the results. So in other words, if your breakthrough times were very short and you had a substantial dead volume, then the dead volume can start to contribute to the errors. But in our case, the dead volumes probably represent, at 10 cc's, the dead volumes are probably only about 10 seconds, something like that. So 10 seconds in a even in a 5-minute experiment is not much. In a 600-minute experiment is pretty insignificant.
Okay, thank you. I think we have time for one more question, Daryl. This one from Marian Alcid. From Marian Alcid, are you performing any desorption measurements during breakthrough analysis?
Yes, we are. I mean, the breakthrough method is quite capable of doing both adsorption and desorption. We didn't show you any desorption ones, but we can certainly run them. And of course, you can also take materials and cycle them. So you can cycle adsorption, desorption, adsorption, desorption. And also, I didn't talk about it, but built into the instrument around the sample, there's a small furnace. So in the breakthrough analyzer, we can locally heat the sample to, I think, 300 degrees. So we can regenerate the sample in situ during the experiment, and then we can let it cool down and run a full adsorption experiment again. So we can both do adsorption and desorption, and we can pre-treat the sample with heat if we need to as well. And in some desorption regimes, heating the sample with adsorbent to remove the materials that adsorb may be required. So we can certainly do that as well.
Great. We do have a few more questions.
Sure, no, I'm fine to talk. Carry on there, John.
Great, fantastic. Another question here from Daryl Jan. If you use a mass spec or FTIR instead of gas sensors, do you need to sample both upstream and downstream?
Right, there's an excellent question. It is most important to sample downstream. You would be smart to have a bypass so that you at least sampled upstream at the start of the experiment to make sure your concentrations are correct. But you could, but if you did an experiment where you just briefly sampled the front end of the column at the start of the experiment to check the concentrations are correct, then you predominantly sat on the downstream measurement. That would be pretty accurate. So I think you'd be good with that. So if it's a near IR, FTIR, yes, that's right. The thing you have to be slightly concerned about is that near IR and IR typically have large gas cells. If you've got low concentrations, you may end up with a large gas cell, and large gas cells take up a lot of volume, so they add a long time constant onto your measurement. So that's the only concern, is that the volume of the measurement that you might need in the gas cell for IR might affect the accuracy of measurements. Mass spec wouldn't have the same problem, although of course they can be less quantitative for concentration determination. So mass spec or near IR or FTIR both have a role. Just a question of thinking about the concentrations and the system structures to make sure you get the right sort of performance. But they would be possible.
Great, thank you, Daryl. And just kind of a general question we've been asked just to finish up, if you can provide any insight. Georgie Tuliev has asked, is there any information about how much CO2 or H2O are consumed by photosynthesis and how much by dissolving in water?
That's a good question. I'm probably not going to try to answer that off the top of my head. I'm sure you could. I mean, I'm sure there are some papers that will give you chapter and verse on that, but I'm not going to hazard a guess. But if someone else in the audience knows that off the top of their head, there, feel free to chat that answer in. I don't know off the top of my head, though. I'm sorry about that one.
No problem. I'm sure we can get back to Georgie afterwards.
No problem.
Okay, great. Well, I think that's all the questions we have for today. So I'd like to thank you again, Daryl, for taking the time. It's really fantastic to have to get this presentation for you, and I'm sure everyone else will thank you as well. Would you have anything to add before you leave?
No, nothing. Thanks everybody for coming and listening. I said, if you have any questions, do feel free to email me. I'm sure myself or Paolo or some of the other researchers in my team would be happy to answer. And thanks for your time and attention today, and take care, everybody. Bye-bye.
Yes, nothing to add on there. Thank you all for attending today. We'll of course be making this presentation available in the next week or so. Please do come check back next week for more educational content. Next week we have the webinar titled Dynamic Vapour Sorption in situ ramen application for the study of hydrate and solvate formation from the presenter Dr. Damiano Cataneo. If any of you do have any more follow-up questions for today's session for Dr. Williams, please do send them through to marketing@surfacemeasurementsystems.com, and we'll get back to you after the session. Thank you all again for joining us today, and I hope you enjoy the rest of your day. Thank you.